And we now continue our investigation. How do supermassive black holes generate energy and how does it get out? First of all, the basic mechanism is that some material has to get down to the deep potential well of the central black hole. As we've seen earlier from numerical simulations, a very efficient way to do this is in gas-rich mergers, whereby gas colliding or interacting galaxies loses energy very rapidly and then sinks to the bottom of their potential wells. This seems to be the best way of fueling the active nuclei, and it's supported by many observations. These are Hubble Space Telescope images of some of the nearby quasars, or really luminous active nuclei. And as you can see, all of them essentially sit in disturbed-looking galaxies, and sometimes you even see companion galaxy. But let's go back to the numbers. So in order to get the observed luminosities, which are of the order 10 to the 44, 10 to the 46 ergs per second, we need really massive black holes, millions or hundreds of millions of solar masses, even billion solar masses has been detected. Now, as the mass is being gobbled up, not all of it is turned into energy, according to MC² formula. So there is some efficiency factor, which I'll denote here as eta, and luminosity is then mass loss rate, or mass accretion rate, m dot times c² times eta. So if you start from very large radii, the binding energy of some chunk of gas far away from black hole relative to a black hole is essentially zero. Bringing it down to the black hole to some radius of r requires energy loss that's given by the formula for the binding energy. Of course, that is if all of the binding energy was converted into luminosity, but it never is, and there is again some efficiency. Now, as you recall from the discussion of Eddington luminosity, it is directly proportional to the mass. So the more massive black hole gets, the more luminous it can get, and that is a recipe for an exponential process. And black holes, provided steady supply of fuel, will grow exponentially. So considering the Schwarzschild black hole, remember that the smallest stable orbit is given by 3 times the Schwarzschild radius, given here, and plugging this into the formula we've seen before, we can see that the net efficiency, maximum efficiency for accretion of black hole is of the order of 17%. This is just oversimplified calculation, and doing this more precisely using general relativity yields efficiency for Schwarzschild black hole of 6%. Now, it turns out that Kerr black holes, the rotating black holes, have smaller, smallest stable orbits, and therefore they can achieve higher efficiency, up to 42% for maximum spin. In reality, it's never that much, and from a variety of studies, we infer that for active nuclei at large, the typical or average efficiency is about 10%. So if we take that and ask what kind of accretion rate is needed in order to power a really luminous quasar, it turns out to be a couple solar masses per year. This is approximately star formation rate over the entire Milky Way galaxy. A couple solar masses per year worth of stars are created in the Milky Way. So what will happen with the material that falls in? It will form an accretion disk, because that's the smallest energy configuration for a given amount of angular momentum. Because it's lost all this binding energy, it will get very hot, and typically the accretion disks peak in ultraviolet or even soft X-rays. And some of that will then emerge as a thermal radiation. The temperature varies with radius, so it won't be simple black body. But some will also emerge as non-thermal radiation, and that's especially if any magnetic fields are present. Theoretical consideration yield the formula that shows the temperature of the accretion disk as a function of radius, as shown here. And as you can see, it depends weakly on the mass accretion rate, m dot, as well as the mass of the black hole itself. And it's almost linear, but not quite, with radius. So Wien's formula, expressed in slightly different fashion, is that peak temperature, at some peak temperature T, the average energy of photons is 2.8 times Boltzmann constant times the temperature. Turns out that the expected temperatures in the inner parts of accretion disks are of the order of 100,000 degrees Kelvin, which means that the peak will be in far ultraviolet or maybe soft X-ray emission. This also means that there will be plenty of ultraviolet photons to ionize gas and even to very high ionization levels, which are necessary to get lines like carbon-4. But the other mechanism is due to the free electrons moving in magnetic field. It's the synchrotron emission. As you probably recall from your study of physics, electric charges moving in magnetic field experience Lorentz force that makes them curve their path. If the charge is accelerated, or rather decelerated in this case, it has to emit some energy. And that is the synchrotron radiation. If the electron does not have a huge energy, we can parameterize that with Lorentz factor, which would be something familiar from special theory of relativity. Then it will move in circles, and that's so-called cyclotron emission. This is how some of the early particle accelerators were working. But if it's really highly relativistic, speed very close to the speed of light or high Lorentz factors, then it will be emitting so-called synchrotron radiation. They have slightly different spectra. Put simply, this radiation mechanism is responsible for all of the radio emission from active galactic nuclei and all of the high energy emission. Thermal is seen from infrared through UV, but there is also synchrotron there as well. But thermal emission does not account for either radio or high energies. Another relativistic effect is that radiation emitted from a moving source, in this case, electron moving in magnetic field, will be highly beamed. It will merge in a cone, and the opening angle of this cone depends on particle energy. The faster it moves, the tighter the cone. So this is what we call relativistic beaming. And we only see the radiation that's emitted in our direction. So what will be the net total emerging radiation depends on the distribution of energies that the electrons have, obviously, because frequency will depend on the electron energy in a given magnetic field. Of course, magnetic fields in these environments are not homogeneous either, so that further broadens the spectrum. And the typical emergent spectrum from active nuclei is power law, or a combination of power laws. This reflects the power law distribution of electron energies. There is also a rollover at really high energies because at some point you run out of energy, and there is also rollover at low energies because electrons can then absorb the photons emitted by other electrons. So it's called the self-absorption cutoff. So it looks something like this. But over large ranges of frequency, it will look like a really good power law. So oftentimes we express that this power is proportional as frequency to some power alpha, which tends to be negative because there is fewer high energy photons. But it's not always as simple. And indeed, when we look at continuum spectra of quasars in ultraviolet, the underlying continuum does seem to be largely described as a power law, although not perfectly. There is a combination of thermal emission from the accretion disk as well as relativistic electrons. So now we can understand the very broad band energy distribution of active nuclei with which we began their discussion. And here it is, plotted over many orders of magnitude in frequency or wavelength. So you see that in the ultraviolet, the soft X-rays, there is a thermal bump from the accretion disk, hot accretion disk. In near to far infrared, there is another thermal component. This one comes from heated dust, for example, from that torus that can be obscuring active nuclei. At very high energies, it's pure synchrotron emission. Sometimes there is also inverse Compton emission. And in radio, it's also pure synchrotron emission. There may or may not be radio emission depending on energy distribution of of electrons, magnetic fields, and so on. Now we spoke about rotating black holes and how threading magnetic field through them or through accretion disk will then end up with magnetic field be tightly wound. That means it'll become very stronger and will be collimated very well along the rotation axis. Now that is exactly how particle accelerators work. The charged particles from surrounding plasma will be accelerated by this magnetic field and will move outward because it's always perpendicular to the local magnetic lines of force, achieving relativistic energies. And this explains presence of jets in active galactic nuclei. Note that if the magnetic field is threading through a black hole, and it could, then that will tap into the rotational kinetic energy of black hole itself. So these fast electrons are carrying mechanical energy. They're simply particles moving at very high speeds, close to the speed of light. And therefore, active nuclei have electromagnetic luminosity, radiation from synchrotron or thermal emission, but also mechanical luminosity. They're releasing a lot of mechanical energy through these fast particles moving out, typically through the jets. And these jets are collimated over a very large range of radii. Here it is in radio for familiar local galaxy of M87. And this is a series of consecutive zooms onto the jet and covers several orders of magnitude in scales. They're collimated because they're moving at relativistic speeds and are very difficult to derail. But eventually they lose enough energy and the plasma that's being carried out by the jet runs into the environment like intracluster gas. And this is where jets then start forming radial lobes. So radial lobes are powered by the kinetic energy brought in by these electrons moving along the jet. And they're emitting synchrotron radiation because magnetic field is also trapped in the plasma. The geometry can be very complicated, but that's the basic physics of it. So jets are very commonly seen in radio sources. Sometimes they're even seen in visible light. Here is the jet of M87, and it corresponds to radio jet as well. Now in some cases we can actually see the obscuring torus. Here is one of nearby active galaxies. The picture on the left shows in orange radio emission superposed an optical image. The picture on the right, confusingly colored now, is the optical image. And you can see that there is a bright central source, but also hidden behind what looks like a little toroidal structure. And the jet, sure enough, is orthogonal to the plane of that obscuring torus, which now, of course, makes perfect sense. There is another interesting phenomenon related to AGN jets, and that is apparent superluminal motions. It was noticed after first precise radio maps were made that some of the blobs that seem to travel along the jet seem to be moving faster than the speed of light, just knowing how far the galaxy is and so on. So how can that be? And there was some discussion of that, whether this is actually physical motion, if relativity is broken, or whether this is just illuminated pattern. You can think of it as if you have a flashlight and you rotate it very fast on some screen far away, the illuminated spot can move faster than the speed of light. But that's not what's going on here. It turns out this is an optical illusion that is specific to relativistic motions. This is a little beyond the scope of this class, but just in case that you're interested to really see in detail, I'm including some slides in your PDF stack that explains how this works. Next, we will talk about high energy, that's X-ray and gamma cosmic backgrounds and their origins, which are largely from active galactic nuclei.